Uh, Hello. I request sharing be allowed, please.
Ma'am, you must have been given you must have been given the access for the.
Colleague, host isn't allowing sharing.
Okay, just a second.
Yeah.
Good evening, ma'am.
Good evening. Good evening. Swati, can you check? I'm still not able to share.
Yes, ma'am. I'm just calling that person. He's not picking up the call. Just give me 2 minutes.
Sure. Thank
Yeah.
you.
Ma'am, will we do questions today for week 5 to 8 or only the
No,
revision?
we will not be doing questions. As in every revision session, this is only going to be a revision at a conceptual level. No specific questions will be taken. Some examples will be given, that's all.
So will be other lectures or not you, any other TAs doing that,
I think, yeah,
taking
that should
questions
be
for
there.
practice?
Yeah, I think that is
Okay,
already
thank you.
scheduled and the TS will tell you about it.
Okay, ma'am, thank you.
Yeah. Yep. Just as we wait for me to get the sharing options, and I think we'll wait for a few more minutes, allow for more participants in case they are joining. Should I leave and join again, Swati, or?
No, ma'am. I'm just asking. Actually, he's not picking up the call, so I'm just trying some other people, like person
Right,
who is there, who can make you the co-host.
right. Thank you.
ये आदमी पागल है क्या?
Now it's over. Yeah,
Okay.
yeah. Thank you. So is it visible? Yeah?
Yes, ma'am. It's visible, ma'am.
Ma'am.
Yes, ma'am.
Okay. Okay, good evening, everyone. This is a tutorial on the topics of permutation, combination, and probability up to the Bayes theorem. Let me, Swati, would you tell the rules or should I just go ahead of that?
Yes, ma'am. So basically, okay, students, the thing is, she will be only telling you the concept and everything, and the question that you have to ask is based upon the concept that she is uh, teaching you. Okay. Other than that, all the doubts will be cleared in the instructor session, which is going to be on Friday. Okay, the mock discussion session. In that, you can ask me doubts regarding other things. Okay, so just be mindful of that. And other than that, please be silent and. If it's a genuine doubt, then only you ask. Okay.
So just good evening all, and just to reiterate, this is not meant to be a doubt clearing session, but with respect to specific examples. I will go through the concepts that have been taught in the topics of permutation, combination, and probability. Definitely, if there is a conceptual level clarity that is needed, the way is after every concept, I'll give some time and then you can ask questions. I hope this is okay so that we can maximize the time allotted to go through the concepts, and then afterwards we will take questions. Okay. After every 5 or 10 minutes, I'll stop for a few minutes and I'll take questions. I hope this is okay with all of you. Okay.
Yes, ma'am.
So what we have planned for today is we will go through again the basic concepts of counting. We'll learn about permutation and combination. And then afterwards, one of the key things that you need to understand when you're learning about permutation and combination is basically when to apply combination and when to apply the permutation part. Then we move on to probability, where we will focus on what is what is a random experiment, what is a sample space, and then we'll move on to the properties of probability, and we'll take to conditional probability, and finally we'll stop with Bayes theorem. This is the plan. So let's get going. So the first thing is, what is the basic principles of counting? Now, why do we need the basic principles of counting? Because permutation is all about counting, and combination is also always all about counting. So one thing that we need to understand is whether we are talking about permutation or combination. Again, the question is, why do I need to know about permutation and combination? The reason is very simple. When we are talking about probability and finding probability of events, eventually when we are setting up a sample space and everything, we do some level of counting. So it's important for us to understand how are we arranging or how are we choosing. That is extremely important for us to understand. So this is a precursor to probability, and hence we are spending time in understanding permutation and combination in greater detail. Now, to understand permutation and combination, we need to understand the basic principle of counting. Now, when I talk about basic principle of counting, again, I have what is called the additional rule of counting and the multiplication rule of counting. Now, addition rule of counting is very simple. It says that if I have an action that can be done in n1 different ways and another action B which can be done in n2 different ways, the total number of ways of the number of actions A or B is n1 plus n2. On the other hand, when I talk about a multiplicative rule, again it says that if an action A can be done in n1 different ways and another action B in n2 different ways, the total number of occurrences of A and B together is n1 into n2. The key difference that you need to notice in the addition and the multiplication rule is, when I talk about addition, it is A or B. I repeat, when I talk about addition, it is A or B, and hence I have n1 plus n2. On the other hand, when I talk about multiplication, it is A and B, and hence I have a n1 into n2. Now I can express or I can extend this, what I talked about two actions to R different actions, as if there is n1 possibilities of the first n2 possibility of the second, and so on. Then there is n1 into n2 up to nr possibilities together for the r actions. This is called the generalized multiplication rule of counting. So a simple illustration is, suppose I have to choose a shirt or a pant. I have 3 choices for shirt and 2 choices for pant. I need to just choose a shirt or a pant. I can either choose a shirt in 3 ways. That is, I can do either a yellow or an orange or a green shirt, or a black pant or a blue pant. Hence, the addition rule says that there are 5 ways of me to choose it. On the other hand, if I have to choose a shirt and a pant, for every shirt I have a choice of 2 pants. So I have a total multiplication rule which says 6 ways of doing it. So the basic difference between addition and multiplication, addition is OR, where I have a OR here, multiplication is an AND. I stop for a minute. Any clarifications here, or is it clear? The basic rule of counting. Any questions? All good? Okay. So with this,
Yes, ma'am, clear.
with this understanding of the basic principle of counting, we establish what is the notation called factorial notation. Again, factorial notation is an important concept when we come to permutations and combination. So factorial notation, I said that when I have R actions in sequence, then N1 into N2 into NR is the general multiplication rule, tells that this is the number of ways I can do the R actions 1 and 2 and R. This is what my multiplication rule says. So suppose I have n blanks. The first blank can be filled in n ways, the second can be filled in n minus 1, third can be filled in n minus 2, and the last blank in one way. Then the number of ways I can fill all the blanks together, first and second and n, is going to be n into n minus 1 into n minus 2 into 1. And this notation is what we call the factorial n notation. By convention, 0 factorial takes the value 1. After factorial, the next important thing we have going to look at is what is a permutation. Any clarification about basic rule and just the introduction of the factorial notation? Okay. So what is a permutation? There are 2 things that we need to understand when we talk about a permutation. One is it is an ordered arrangement. So the notion of an order is extremely important, and we are talking about a permutation as an ordered arrangement, or in other words, we are telling that I'm looking at a particular way of arranging. So you have both order and arrangement. For example, again, if I have 1, 2, 3, 4, 5, 6 up to R blanks here, the number of ways I can fill this is n ways. Once I fill this in n ways, the number of ways I can fill this up is in n minus 1. This will be n minus 2. The rth is going to be n minus r plus 1. And the total number of ways I can do this is n into n minus 1 into n minus 2 into n minus r plus 1. This is what we say is the total number of ways of permutation of R objects from a collection of n objects. This is what we write total. This is a notation. Total number of possible permutation of R objects from a collection of n. Here I have these n as distinct objects. Very important to understand that any formula is as good as what you assume. This distinct objects is very important here. So now I am defining this NPR as n into n minus 1 up to n minus r plus 1. I can do one thing. I can multiply and divide this with n minus r factorial. So I see that my numerator is just n factorial. My denominator is n minus r factorial. To give me this NPR is n factorial divided by r factorial. So the first formula that you have in permutation is the definition of what your NPR is, and that is what I have as n factorial by n minus r factorial. What is the condition? The condition is these objects are distinct and repetitions are not allowed. I repeat, the condition is objects are distinct and repetitions are not allowed. Because repetitions are not allowed, if the first blank can be filled in n ways, the second can be filled only in n minus one way, because the one way is going here, and the rth blank can be filled in n minus r plus one ways. The special cases are NP0 is equal to 1, NP1 equal to n, and NPn equal to n factorial. So this again, just fill in r equal to 0. What this means is if NP0 is equivalent to, there is just one ordered arrangement of no objects. There are n ways of choosing one object from n objects. So if I have 5 objects, I can choose one from 5 in 5 different ways. So in general, NP1 is equal to n, and NPn is same as n factorial, or NPn is equivalent to arranging n distinct objects in is n factorial. Any questions here? Any clarifications or questions about permutations when objects are distinct and repetitions are not allowed? Any
No, ma'am.
questions?
All good.
All good? Okay. The next thing is, okay, objects continue to be distinct, but now I'm allowing for repetitions. So what is happening here? What was n minus 1 here is I'm having n. All the n are allowed for me. Is that clear? That is the key difference. In the earlier case, I was not allowing repetition. So if one object is already filled, I don't have that available for choice in the second. Whereas here, when I'm allowing repetition, I have a n into n into n into n. How many times I'm multiplying it? R times. So I have n to the power r. So what is the number of possible permutation of r objects from n distinct objects? When repetition is allowed, it is n to the r. Is this clear? Yeah.
Yes, ma'am.
First is when repetitions were not allowed. The second is when repetitions are allowed. Now, what is the third case? The third case we are going to look at is, first we saw that when objects were distinct, I looked at, so first one was objects n distinct objects, repetitions not allowed, repetitions allowed. Okay. Now, what would happen when n itself, I don't have distinct objects? So distinct object typically is, I will ask, how do you arrange people in a row? Okay, they are distinct. Okay. Then after I want to have a choice of passcodes. I can tell that I'm not allowing repetition, I'm allowing repetition. So that is how you can, in the context of the problem, you can find out whether it is distinct, whether I'm allowing repetition, not allowing repetition, or whether I am allowing repetition. Now, what would happen if the objects are not distinct? For example, I have n objects, okay, of which p of them are of the same kind. I repeat, I have n objects of which p of them are of the same kind. For example, I have data. Okay. How many objects do I have? 4, of which 2 of them are of the same kind. So whether, if I label this A1 and A2, DA1 TA2 is the same as DA2 TA1. Would you agree? Just for my convenience, I put it as A1 and A2. But technically, this whether A1 comes before A2 or A2 comes before A1, it is the same A. Is that clear? Yeah.
Yes, ma'am.
Yes, ma'am.
So what we are going to do here is when I have this P of them of the same kind. So in this example, n equal to 4 with 2 of them of the same kind. When I have distinct, then the way I had written this was n factorial. So now it is going to be n factorial divided by P factorial. Now suppose I have again n objects. I have P1 of one kind, P2 of another kind, Pk of kth kind, then I know the total number of permutations is n factorial by P1 factorial, P2 factorial, Pk factorial. This notion of n divided by P factorial, where I had only one object of one kind, I can extend it to P1 of one kind, P2 of one kind, Pk of n kind to get this formula, which says that when you have n objects which are not distinct, and I have P of one kind, it is n factorial by P factorial. And when I have P1 of one kind, P2 of one kind, and so forth, it is going to be n factorial by P1 factorial, P2 factorial, Pk factorial. So in summary, when you're talking about permutation, then we need to understand the following: whether my objects are distinct. If they are distinct, then am I allowing repetitions or I'm not allowing repetitions? If my objects are not distinct, then how many are of one kind, how many are of the other kind? For example, statistics, what would be my n? My n would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. My n is 10. I have P1. How many S's do I have? I have 3 S's. I have 3 T's. I have one A, I have 2 I's and 1 C. So the total number of ways I can arrange this word is 10 factorial by 3 factorial, 3 factorial, 1 factorial, 2 factorial, and 1 factorial. Okay. Any questions to this? And these are all what we refer to as linear permutations, because I'm talking about arranging all of them in a line. Any questions? Is it clear?
Yes, ma'am.
Yes, ma'am.
Right. So the next thing that we learned in our conceptual understanding or in the course was the notion of a circular permutation. Now, all of this, what we said was arranging people in a line or arranging objects in a line. For example, if I have 3 people, I can arrange them in a line A, B, C. Okay. A, C, B, B, A, C, B, C, A, C, A, B, and C, B, A, which is 3 factorial. And I know 3 factorial is 3 into 2, 6 ways. Okay. But now, instead of arranging them in a line, if I were to arrange them in a circle, would you all agree that A, B, C in a circle is the same as B, C, A, which is the same as C, A, B? Would you all agree? Whether I'm up, see,
Yes,
A, B, C is same as B, C, A, which is same as C, A, B. Would you all agree this is true or not?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
So the notion is, I don't have the same number of circular permutations as I had in the number of linear permutation. So the question is, what is the number of circular permutations and how can I get the number of ways in which n distinct objects is arranged in a circle? Now, one way to look at distinct objects arranged in a circle is first I look at whether the clockwise and anti-clockwise are same or different. So the first thing I'm looking at is anti-clockwise and anti-clockwise are different. What do we mean by that? This is A, B, C, D. Okay. Now this is different from A, D, C, B. This is the anti-clockwise. This is the clockwise arrangement. Okay. Similarly, AC, this is the clockwise arrangement. This is the anti-clockwise arrangement. So I'm considering these two arrangements differently. Is this clear? The clockwise and anti-clockwise are different.
Yes, ma'am.
Right. So now, how do I know the number of ways of fixing it? So what we do is you fix one of them. So if I fix one of them, the remaining, how many do I have remaining? Here I have totally 4 objects. If I fix A, the remaining of them, so if I fix A, I can have a B, C, D. I could have a C, D, B. I could have a D, B, C. I could have a B, D, C. Okay. I could have a C, D, B, D. Okay. With a C, I could have a BD, and with a D, I could have a CB. So you can see that once I fix this A, the number of permutation of other things is 3 factorial. I repeat, once I fix this A, I'm interested in knowing how many ways I can do the remaining permutation. I'm looking at it, okay, you fix one, and the remaining thing is going to be a linear permutation of the number of ways I can arrange this, and I'm going to finish the loop. But this is fixed. So I get if the clockwise and anti-clockwise are different, the total number of ways n distinct objects can be arranged is in n minus 1 factorial ways. Now, where would this be useful? Many a time you'd be asked that, okay, how many ways can I seat people on a round table? So when I want to seat 4 people on a round table and the clockwise and the anti-clockwise conditions are different, then that is going to be n minus 1 factorial. Now you keep adding layers of complexity to this. I'll say that 2 people do not want to sit together. How would you look at it? The same thing. It is going to be, again, I fix this. Suppose B and C are not going to sit together. I look at the total things in which B and C appear together, and I remove that from the total number of permutations. So even in the linear permutation, when you say that I want to arrange 4 people such that 2 people never appear together, you look at all those permutations where 2 people appear together and the total number of permutations, and you subtract it to get the number of permutations when 2 people will never be seated together or will be seated together. Okay. The same logic you apply in the circular permutation case also. On the other hand, if I want to look at clockwise and anti-clockwise are actually same, in this case, it is just going to be n minus 1 factorial by 2, because for every clockwise and anti-clockwise is repeated only once. So I have it as n minus 1 factorial by 2. Any questions on the conceptual understanding of circular permutation?
No,
No,
ma'am.
ma'am.
Clear.
Right?
No,
All
ma'am.
clear.
So the things that you need to see is, obviously the questions are not going to be just plain applications, but whenever you are presented with a problem that requires permutation, you look at whether the objects are, first of all, you ask the question, is it linear or is it circular? Are objects distinct or objects not distinct? If objects are distinct, are repetitions allowed or not allowed? Everything. And then you have the formula for it. Same thing here. Is clockwise and anti-clockwise same or clockwise, anti-clockwise different? And then you can apply the formula to get hold of the answers. This is a very simple, structured way of understanding whether you what is it that you have to apply. Now, moving forward, this is what we looked at, permutation. Now, on the other hand, a combination is, again, it is a combination of R objects from N objects is what we are interested in knowing. So what is a combination? In a combination, the order is not important. So what is most important is Again, I had looked at n distinct objects. I said number of possible ordered arrangements is what I said was my permutation. On the other hand, when I'm looking at a combination, I'm looking at the number of possible combination of R objects from a collection of n distinct objects. What do we mean by this? For example, let's look at A, B, and C. Okay, I can have in this, suppose I'm looking at two objects, okay, from three objects, my n is equal to 3, my r is equal to 2. What would be my NPR? My NPR is going to be, okay, my NPR. NPR equal to 3P2, which is 3 factorial by 1 factorial, which is just 6. Till here, is it clear? Yeah,
Yes, ma'am.
right?
Yes,
Now,
ma'am.
see what happens is when I have 3 and I'm choosing two objects, AB is distinct from BA when the order is important. On the other hand, when order is not important, these two are the same. So the way we always think is, suppose I'm choosing two people to form a committee. I just want two people. So I can choose two people. I can either choose AB, or I can choose AC, or I can choose BC. On the other hand, if I want to again say that I'm choosing two people such that one is a president and another is the vice president, A being president and B being vice president is different from B being president and A being vice president. Would you agree? So here
Yes,
I'm
ma'am.
just choosing two people, A and B. But when I'm arranging and the order is important, it is A, B and B, A are different. So in other words, for every, that is the number of possible, so each combination, okay, gives rise to R factorial. So I have a combination here which is giving rise to 2. So if I have ABC as a combination, it would be ABC, it would be ACB, it would be BAC, it would be BCA, CAB and CBA. So each combination gives rise to R factorial arrangements. So what is happening? So for if I'm looking at number of possible combinations of R objects from N, okay, I know that each combination gives rise to R factorial arrangements. I know NPR is the total number of arrangements of N objects from R. Each combination gives rise to R. So NPR is a total number of arrangements is R factorial into NCR, which is giving me NCR is N factorial into N minus R factorial 1 by R factorial. So this is the formula I have for NCR. The key idea that relates the prime combination to permutation is this. That is, if you have a combination, so AB is a combination. It is just choosing two people. This is giving rise to AB and BA, 2 factorial. ABC is a choosing. This is giving rise to 6, ABC, ACB, BAC, BCA, CAB, CBA. So each combination gives rise to R factorial arrangements. So the way I can relate the NCR is NCR equal to 1 by R factorial, and this is NPR, or NPR equal to R factorial into NCR. Is this clear? What is the binomial, the combination formula, and how is that related to the permutation formula? Is this clear?
Yes, ma'am.
Right? Yeah.
Ma'am, I have a doubt.
Yes, please.
Ma'am, in the practice assignment, there was one question. There were two circles, inner circle and outer circle. And for inner circle, we had used permutation. And for outer circle, we did not use the formula for circular permutation. Instead, we use it for linear permutation. So I did not understand this concept, why linear permutation was used. And the TA said that just because the position is fixed with respect to inner circle, we are using here linear permutation instead of circular permutation.
Yes, I do not know what is this question. Okay, so Swati, can you take this question and explain?
Yes, ma'am. So,
Right.
Yadav, Snehal, we will just clear your doubt in the next session, instructor session. Okay?
Right, because I do not
Okay,
know
ma'am.
the reason. I should not be telling something which I am not aware of. Okay, but whatever it is, you need to understand. So this is a very specific question as to why something is taken as circular and why something is taken as linear. If you don't get it addressed in the next session, you please raise it again in the discussion forum. We will try and address it. Okay.
Okay, ma'am.
Right. So now the next question that we are going to look at is so sometimes some combinatorial properties become very important. The first combinatorial property says n choose r is n choose n minus r. Now let's understand what it is. Suppose I'm choosing 3 objects from 5 objects. Okay. Suppose I'm choosing 3 objects from 5 objects. Would you all agree that it is equivalent to not choosing 2 objects from 5 objects?
Yes.
Okay. So that is what this says. So choosing r from n is the same as not choosing n minus r from n. So that not choosing n minus r from n is n choose n minus r. Choosing r from n is n choose r. And that is, both of them are same. That's what this combinatorial identity says. Is that clear? And you can mathematically verify that also.
Yes, ma'am.
Is this clear? Okay. Now the next thing is choosing n objects from itself is again 1. Suppose I have only 3 people. How many ways can I choose 3 people from 3 people?
One way.
Only
Only
one
one
way,
way.
right? So choosing 3 people, n choose n is equal to 1. Now the next thing is n choose 0. What does this mean? I know not choosing anybody from 3 people. That also I can do only in one way. So that is what n choose n equal to 1 and n choose 0 is equal to not choosing anybody. Okay, either I choose all of them or I don't choose anyone. That can be done in one way. Now what is the next very
Can we say, ma'am, like
Hmm.
NC, N minus R, is like a complement of this NCR?
We have not, see, I am very careful not to define complement because complement is typically you're looking at it when you're talking of it from a set perspective, right?
Yes.
Now, what is a set here? I don't have a set here, right? Even though you can talk about actions as complementary, we have not been defining it as a complementary action. So that's why I said choosing R people, the complementary action is not choosing n minus R people in some sense.
Agree.
Is that clear?
Yeah.
Okay,
Thank you.
without the set concept, I can think about it in that way. Choosing R, that is choosing 3 people from 5, is equivalent to not choosing 2 from 5. That's what I'm trying to say.
Right.
Right? Okay. The next identity is this identity which we have as n choose R is n minus 1 choose R minus 1 plus n minus 1 choose R. Again, let's look at it from a very intuitive point of view. N choose R says I'm choosing R objects from n objects. Okay. Now let me fix one object. There are 2 things in this n choose R. Either that object is there or that object is not there. I'm choosing any one object. Is that clear?
Yes, ma'am.
Okay.
Yes, ma'am.
Right. Now, if that object is there already in the choice, this n choose r is I have n objects and I'm choosing r objects. I'm choosing some object. I'm fixing an object. And I'm trying to say that, okay, among this choice, that object is there, it is not there. If that object is there, what is remaining? I have to choose r minus 1 from n minus 1. Would you agree? Because this object is already there.
Yes, ma'am.
I have only
Remaining
n
item.
minus 1 objects remaining and I have to choose r minus 1 from that. Is that right? So it is
Yes,
either
ma'am.
there or it is not there. So if it is there, the total number of ways of choosing the remaining r minus 1 is n minus 1, choose r minus 1. Would you all agree?
Yes, ma'am.
Yes, ma'am.
Now, if it is not there, okay, then I have to choose this r from n minus 1 because it is not there. I have to choose all the r because if it is there, then I have to only choose r minus 1 because this rth object is there. So the remaining I have to choose is only r minus 1. But if this r is not there, I have to choose all the r. But I have only n minus 1 from which I choose because this rth object is not there. So I have only n minus 1 remaining to choose these r objects. So I know that n choose r is n minus 1 choose r minus 1 plus n minus 1 choose r. Is this clear how we have got it? Or should I?
Yes, ma'am.
Is this
Yes,
clear?
ma'am.
Fix some object, either it is there or not there. That's why because I'm saying it is there or not there, it is an addition. And if it is there, the number of ways I can choose the remaining r minus 1 is n minus 1 choose r minus 1. If it is not there, I need to choose r, but I have only n minus 1 from which I choose it. So the total number of ways of choosing r from n objects is n minus 1 choose r minus 1 plus n minus 1 choose r. This is a very important combinatorial identity. Any questions? Any questions? Is it clear? Yeah.
Yes, ma'am.
Yes,
Clear.
ma'am.
Yes, ma'am.
Now, once you have an idea of the results, one of the key things, applications that you'd be tested on is to see whether you can apply the permutation or combination. So the key idea here is wherever order matters, permutation. Wherever order does not matter, combination. Okay. So wherever order matters. So now let's look at certain things. I need to create a password. Is it a permutation or a combination?
It's a permutation.
Ma'am, permutation.
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 Okay,
Because
I'm not asking how many, I'm just trying to find out whether we can identify it as a permutation or a combination. Okay, the next one. A pizza parlor is offering a build your own pizza with a choice of 5 different toppings from 10 different toppings. So you can see if you all have ordered food on Swiggy, you can see that it gives you an option, choose any main course, choose any appetizer, choose any this one roti and all of that, right? So total number of unique topics, what would it be? Combination or combination?
combination.
Combination.
Combination, ma'am.
Combination.
Combination.
Because
Combination.
order doesn't matter here, right? I'm just choosing 5 topics, not what on top I'm going to put. Okay. Forming a 4-digit PIN code.
Permutation.
Order matters.
Permutation.
Right? A bookshelf has 8 different books. I want to arrange these books. Permutation or combination? Arrange.
Arrange a permutation.
Permutation.
Arrange, permutation.
Permutation.
I want to just choose
Then
Combination.
combination. Okay. Right? Very good. So one of the things where you would have seen a lot of application is formation of teams. What do we mean by formation of teams? So suppose I have 10 people and I'm choosing a committee of 4 people. Will it be a permutation or will it be a combination? Does the order matter here?
Combination.
Combination.
It's a combination. Order does not matter. On the other hand, if I am forming a committee where I need people to hold specific positions, then it would be order matters here. So what will it be? It would be a
Permutation.
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 Right? So
Yes,
again,
ma'am.
a 4-pin code, we have already seen it is a permutation. So the key differences between a permutation and combination is, in a permutation, order matters. In a combination, order does not matter. The formula for picking up R object from n distinct object is NPR, n factorial by n minus R factorial. On the other hand, combination of R objects from n distinct object is NCR, which is n factorial by R factorial into n minus R factorial. This is the basic formula. We have seen what happens when objects are distinct and repetitions are allowed. Objects are not distinct and circular permutation. This is about permutations and combinations at a conceptual level. Any questions, clarification, doubts?
Ma'am, I have a question.
Yes, please.
Actually, I have a doubt about circular permutation. So, like, if I have like 5 people, right, and I am asked to arrange them in a circular manner. So, like, in that case, does the anti-clockwise and clockwise are different or they are same?
See, when typically you're talking about people, right, the anti-clockwise and clockwise would be different, right? So you look at it, these are, imagine these are four people, right? When
Yes.
is the difference? See, these two, okay, this ABDC and ABCD, the clockwise and the anti-clockwise are different. What is this arrangement? Here, A is next to B is next to C is next to D. In this way, this arrangement is, now you ask, are these two different or not different when they are sitting around a table? You answer the question. 4 people sitting around the table.
They are different.
You got your answer, right? On the other hand, if these were colored beads, okay, in a sort of, I'm making a bracelet. Okay. Now you tell me whether they would be same or whether they would be different.
They will be same.
How and why?
Because the beds are identical.
Pardon?
Because the beds are identical.
I'm not saying, I'm again telling you the distinct objects is what I have taken here, right? So I have a red bead, blue bead, green bead, and yellow bead. Okay, and I'm putting it in a bracelet or something.
Then it will be different.
It depends on what you're doing, right? With the beads also, right?
Yeah.
They're not equivalent to people, but I'm talking about the arrangement.
Then it will be different.
Will it be different? Just think about it. Okay. So you can see that one way is this and this. When there are people sitting in a round table, they are definitely different. Right? But when I'm looking at, say, the same type, when clockwise and anti-clockwise are not different, okay, and then it depends on the context. If you look at the context and look at the arrangement, you can figure out whether it is a different or non-different. It depends on, again, what you are looking at. Is it clear?
Okay, got it.
Right? Okay. So now the next thing is we move on to probability. The first thing is, whenever we talk about probability, we start with the basic building blocks of probability. Now, what are the building? Yeah?
I have a doubt.
Yes?
Ma'am,
Yeah, please go ahead.
I always get confused when I have to use multiplication rule of counting or permutation.
Or permutation. Can you give me an example?
Example like Vinod has 3 register and 6 cover paper of different colors. In how many ways can he cover all the register with cover paper?
I didn't get the question. Can you please repeat it?
Question, Vinod has 3 registers and 6 covers paper of different colors. In how many ways can he cover all the registers with cover paper?
Okay. So what is your question here?
My question here uh, is
See, first of all, you need to understand that the permutation is also counting only. Do you understand that? Permutation also, you're counting the number of ways of doing certain things. Even in your combination, you are doing a number of ways of doing certain things. Is it right? Okay. Even your basic formula of permutation, which was n into n minus 1 to n minus r plus 1, was an application of the multiplication rule of counting. Okay. So the whole idea of applying multiplication rule of counting is, if I have a sequence of actions that are being done, then the total number of ways of doing all the actions together is n into n minus 1 into n minus r plus 1. That is how I got the formula NPR. Okay. And the same thing as when repetitions are allowed, the first block can be filled in n ways, the second also in n ways, the rth in n ways, so I got n to the power of r. All of them were applications of multiplication rule of counting. Is it clear? So, I am not getting the question as to when would you use multiplication rule and when would you use permutation. Permutation itself is an application of multiplication rule of counting.
okay, ma'am.
Okay, right.
Ma'am, if I may ask a question,
Yeah, please.
suppose we have like five MCQs, of
Okay.
which there are
Mm.
3 options.
Mm.
So ideally, what my approach was 5 to the power 3.
The
So
power of?
5 to power 3.
But what is the question? You have 5 multiple choice and 3 options.
3 option.
What is
So
the question?
here we know like we have to apply n to the power r
Okay.
formula. So most of the time I make mistake in such questions. So if you can clarify, if you can
See,
take that.
the idea is, see, this requires a bit, that's why we ask you to practice it. Every time, see, I would suggest that the key things are, first of all, you see whether they are distinct. Okay. If they are distinct, here you're talking about 5 MCQ, definitely they are distinct. Right? N is distinct. Even before that, identify what is your N and what is your R. Okay, from the question. Now, once you identify what is your N and R, find out whether this N is distinct or it is not distinct. If it is distinct, then are you allowing repetitions or not allowing repetition? So once you start mapping every question to what you have already, then you would just apply the formula. Rather than just blindly applying the formula, you look at where does the problem, what is the characteristic of this is what we say is the characteristic of a problem. Am I talking about n distinct objects? Am I talking about n non-distinct objects? Am I talking about repetitions allowed? Am I talking about repetitions not allowed? And then I apply the formula. Is it clear? Look
Yes,
at the
ma'am.
characteristic of the problem and then apply the situation. Is this clear?
Yeah, ma'am. Thank you.
Right? Go about in a structured way. And mostly that should help you. Okay?
Thank you.
Excuse me, ma'am. May I
Yeah.
ask you a question?
Yes, please.
Madam, so during the exam, what are the ways which the questions try to trick you, madam, like during stats?
I
Like
don't think
the concept is pretty
Uh,
much straightforward, but during the exams, they test your concepts by asking tricky questions. So, what are the ways by which I can prepare accordingly? Because
no, the simple thing is try and answer as many questions as possible. Don't restrict yourself to only the questions that are being discussed in lectures or your tutorials or anything. You have umpteen books, umpteen things available now, and now you people have an overload of information that is available, right?
Yes, ma'am, but I can't if I study too much, then I may study something that may come out of syllabus.
No, see, I think focus on again applying a certain framework or certain characteristic. It should work most of the time. Okay.
Okay,
I don't
fine.
think there is any algorithm how I can tell you that or any trick to tell you how to solve it, because this is not pattern recognition. This is a very structured way of thinking. Okay.
Okay, ma'am.
Right? Okay. At least I am not aware of anything where I can help you answer tricky questions or something. Okay, because my role as a teacher is to teach you concepts, not to teach you pattern recognition and how you crack an examination. Okay.
That's fine, ma'am. I'm just asking because doing the
I
exam
think
we are expected
I
to
have
solve
never
questions.
thought about it in that perspective, so I am not able to answer it. Okay. So when
All right, fine.
okay, right. When I move on to probability, the key building block of probability is the notion of a random experiment. Now, the idea is, suppose I just give you suppose I'm asking you to perform an experiment where I'm giving you a 5 kilogram block and a 3 kilogram block. Okay, no matter who is doing this experiment, what would be the result? I'm asking you to just say I'm giving you a 5 kilogram packet of sugar and a 2 kilogram packet of sugar, and I'm asking you to mix these two. What would be the result of this experiment?
Either you are cutting the 3 kg packet and mixing it into the
No,
5.
I'm just telling you, I'm giving you a 5 kilogram and let me tell you 3 kilogram. Forget about 2 kilograms. I did a mistake. So 5 kilogram and 3 kilograms of sugar, and I'm asking you to just mix this two. So what would be the result?
7
Ma'am,
grams
8
of sugar.
kilogram. 8 kilogram of
5 and
sugar.
3, it is 8 kilogram. Now, would this depend on the person doing the experiment, or it is independent of the person who is doing the experiment?
Ma'am, independent.
Dependent on the person doing the event.
On the other hand, if I give you a 10 rupee coin or a 5 rupee coin and ask you to toss the coin, what would be the outcomes of this experiment?
It varies
Heads or
from the
tails?
user.
Heads and tails.
Yes, head
Uncertain.
tail. So there is an element of uncertainty in what it comes, and this is dependent on the person who is doing. It is not dependent on the person, but you can see that the outcome of this experiment is uncertain. So there are two things. One thing is a common mistake made by many people is saying that a random experiment is an experiment where the outcome is not known. This is incorrect. A random experiment is an experiment where the outcome is uncertain. That is, I cannot predict what is the outcome, because when I toss a coin, I know the outcome would be a head or a tail, but I do not know which of these outcome is actually going to be there. So the uncertainty is the outcome is not predictable with certainty. On the other hand, when I am mixing 5 kilos with 3 kilos, I know for sure I'm going to get 8 kilos. There is no uncertainty there. So this is what is called a random experiment. It's an experiment in which the outcome is not known with certainty. So if the outcome is not known, then I set up what is called the sample space, which is the set of all possible outcomes. So the next building block of my probability is the notion of a sample space. What is a sample space? It is a collection of all basic outcomes. If I toss a coin once, the sample space is H and T. If I toss a coin twice, my sample space is HH, HT, TH, and TT. If I toss a coin till I get a head, what would be my sample space?
Same.
What same? No. Listen to the experiment. I'm going to toss a coin till I stop the experiment the minute I get a head.
It will be infinite.
So what
No,
would be the
it's
sample?
uncertain. Like we
what-
cannot guess.
No. What are the sample? What are the possible outcomes?
How many coins are you tossing?
Only one coin. And I'm stopping it the minute I get a head.
At most,
So what
Second,
would be the
Heads and
possible
then
outcome?
Once or twice.
I'm tossing a coin and I'm stopping the experiment the minute I get a head.
either you can get it in the first event or the second,
Okay, I
third,
can get
fourth,
a head in the first, or in the second,
second,
or in the
or in
third,
third.
or in the fourth. So it keeps
Yes,
going. Is
keeps
that
on going.
clear? Is that clear?
Yes, ma'am.
Yes.
Right? Okay. Again, so this is also an uncertain. Is this a random experiment or is it a deterministic experiment? It is a random experiment.
randomist.
Right. Now I'm leaving from home and the outcome is the time taken for me to reach my office. Is it a random experiment? Is it a deterministic experiment?
The determinant.
It's a deterministic.
Deterministic.
You can reach by that time particularly.
How can if I get a traffic, so I might get late.
Yeah. So is it so deterministic that every
No.
time I leave at 8:15, I know for sure that I reach by 8:30 in my
No,
office?
it is
No,
not.
no, no.
What is it?
No.
Is it a random experiment? If so, what are my outcomes? So I'm telling the time taken. So the minute I say it is a time taken, what is my tracking? So it is going to be anything. It could be 0 minutes. Time is continuous, right?
Yes.
Yes.
So you can see that the sample space is a collection of all basic outcomes. So the first thing that you need to understand is how do I, first of all, identify the random experiment? And the second thing is, how do I list the outcomes of my sample space? Is this clear?
Yes, ma'am.
Right?
Yes, ma'am.
Now, when I talk about basic outcomes in a random experiment, the two things which are very important for me is they are mutually exclusive and collectively exhaustive. What do I mean by this is, for example, when I toss a coin, what are the two basic outcomes? It is either a head or a tail. Now, what do I mean by mutually exclusive? The occurrence of one excludes the occurrence of the other. Okay, so if I get a head, can I get a tail also?
No.
No, ma'am.
So only one of them can occur, and their collectively exhaustive means that at least one of them should occur. I cannot toss a coin and say that it is neither a head or a tail. Do you see that? So that is what we mean by mutually exclusive and collectively exhaustive. Is that clear?
Yes, ma'am.
Right? So this is about the basic notion of a sample space. The other building block is what we refer to as an event. Let me take an example of rolling a die. What is the sample space I have here? If I roll a die,
1 to 6.
1, 2,
1, 2, 3, 4, 5,
4,
6.
5, 6.
5, 6. I can define an event to be an odd outcome. What would that be? It would be just 1, 3, 5. I can define an event to be an even outcome, which is going to be
2, 4, 6.
and 6. Okay. And you can see from the way the sample space is a subset, all the events are subsets of the sample space. Okay. Now, this notion of sample space and events helps us to, again, because I've defined the event as a subset, all these set operations that I know, what are the basic set operations?
Union of sets and intersection of sets.
Intersection. What about complement?
Yes, ma'am. Complement.
Yes, complement.
The basic is union and intersection. So let's look at the example where I'm tossing. So I'm tossing two coins. What is the sample space?
Head,
Head, tail, head, tail.
Head.
Yes.
Head, tail.
Head, tail, tail, head.
Tail, head, and tail.
Head in the first toss.
Head, and head, tail.
Head, tail. Head on the second toss.
Head, tail, head.
Tail, head. Head on the first or second toss.
First,
Head, head.
Head,
including the
tail, head.
And TH.
TH.
Acha, first.
Head on the first and second toss.
H.
Okay. So this is my sample space. This is my even. This is my E2. This is my E3. This is my E4. Okay. So now you can see that you have all of them are subsets. What you can notice is, are E1 and E2 disjoint? No, right?
No,
What is
no.
common for all the E1, E2, E3 and E4? Which
HH.
even, which outcome?
HH.
HH. Right? So you can see that if I am asking questions, I might be interested in knowing about E1 and E2. This third event, which I defined as E3, was nothing but E1 union E2. And the fourth event was nothing but E1 intersection E2. Is that clear?
Yes, ma'am.
Okay. So now the next thing that we are interested in knowing is the notion of a null event. So if there are no outcomes in a experiment, that is, if an event has no outcomes, it is called a null event. If intersection of E intersection F is disjoint, so sorry, if it is a null event, then I say E and F are disjoint or mutually exclusive events. This is again a definition. The next thing we said was union, intersection, and complement. So I can define the complement of a set as all those outcomes in the sample space that are not contained in E. For example, let's look at again S equal to HH, HT, TH, and TT. I am defining an event to be HH and TT. Now, how would I articulate this event E? How would I describe this event E?
Same outcome on both tosses.
Same outcome on both the tosses. What is the complement of this event?
HT and TH.
HT and TH. Describe that event.
Different outcomes
No,
on both
no two outcomes would be same.
So E complement is HT and TH, which is the same as the both outcomes of the tosses are different. They are not same. Okay? Is it clear? So I can say that E complement occurs only if E does not occur. If both the tosses have same, I cannot have E complement. That's what we want to understand. Okay. And another important notion that I have is the complement of a sample space is the null set. Okay. Now experiment. Let me give you certain things. You can try it out now. Let the experiment be toss a coin once, note the outcomes. What is the sample space?
Head and tail.
Toss a coin twice. Let me, the sample space we know. The first event is head on the first toss. What is, if the event is head on the first toss, what is the event? Here.
Head, 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 tail.
Head, tail.
Two
What is
events.
the complement of this event?
Tail, head, and tail.
Tail.
Tail head and tail.
Tail head and tail. How would I describe this event? What is the complement of head on the first toss?
Tail
on the
on
first
the first toss.
Tail on the first toss.
Tail on the first toss. Is it clear?
Yes, ma'am.
So that is what you need to understand is what is the complement of an event. Again, since we have defined events as subsets, for any two event, okay, if all the outcomes in E are also the outcomes of F, then we say that E is contained in F. Again, let's go back to the tossing two coins. Head on the first toss is HHHT. Head in both the tosses is E. I know that this E is contained in this F. So E is a subset of F. Okay. So this is, again, if I have all outcomes in E is also in F, then I say E is a subset of F or E is contained in F. So now we'll go back. Since we have discussed the events and the sample space as sets, we can borrow the notion of Venn diagrams to describe the sets. Now I know that the sample space can be this equivalent to my universal set and it can be represented by a large rectangle. The events are the the subsets of the sample space, which can be represented by smaller circles. For example, I have an event E, I have an event F, and these are represented by the smaller circles. If I have two events that are, so if you look at the union, the entire shaded region is a union, whereas this which is shaded in blue is the E intersection F. If they are disjoint, I have these two which do not have any intersection. Okay. Again, subset, all of this discussed in the earlier section is what we have discussed here. Here I have E is a subset of F. Now let's move on to the main idea of assigning probabilities to these events. Now what the probability axiom says, I have already had a random experiment. For any random experiment, I have a sample space. Now for every event in the sample space, I'm assigning a probability of that event and I'm denoting that by P of E. This P of E is the probability of an event happening. What the axiomatic approach of probability says is, this probability of E follows three axioms. What is the first axiom? For any event E, the probability of this E or the probability of an event happening is a number between 0 and 1. The second axiom says that the probability of the sample space is 1. In other words, what this indicates is the outcome of a experiment will definitely happen, will be an element of the sample space. And the third is what we refer to as the countability axiom of probability, which says that if I have a sequence of mutually exclusive events, I repeat, if I have a sequence of mutually exclusive events, then the probability of the countable union is the sum of the probabilities. This axiom says that the probability of a countable union is the sum of the probabilities. I can look at it as the probability of a finite union is the finite sum of probabilities also. This is what is referred to as an addition rule. But the addition rule here needs mutually exclusive or disjoint events. So the question is, what happens if I have non-disjoint events? So what it says is, if I have two disjoint events, the probability of E1 or E2 happening is the sum of the probabilities. What would happen if my events are non-disjoint? So I have a E1 and E2 which are not disjoint. So I can look at this as three different disjoint areas. One is this blue area. Okay. One is this. So you can see that. One is this orange area. And one is this green area. The orange, blue, and green are disjoint now. Would you all agree? Right? Yes. So I can write this E1 union E2 as the orange union blue union green. Would you all agree with it?
Yes, ma'am.
Right? Now, but what I know is this probability of E1 union E2 is probability of orange union blue union green. But are orange, blue, and green disjoint?
Yes, ma'am.
So I can apply the rule or the axiom to get this as probability of orange plus probability of blue plus probability of green. Can I do that?
Yes, ma'am.
But what is probability of orange alone in terms of this? So probability of orange is probability of E1 minus probability of blue.
Yes.
Yeah?
Yes.
So this is probability of E1 minus probability of blue. I retain probability of blue as it is. What is probability of green?
E2 minus the blue one.
Probability of E2 minus probability of B. So these two will cancel to give me that probability of E1 union E2 is probability of E1 plus probability of E2 minus probability of E1 intersection E2. And this is what we know as the addition rule of probability, which says that the probability of the union of two events is probability of the sum of the probability minus probability of E1 intersection E2. Now you can look at this and extend this for 3 events also, but the idea is the same. Now, 2 more things is the probability of the complement is 1 minus probability of E and the probability of the null set is equal to 0. All of them follow from your general axioms of probability. For example, let's apply to an example. A customer goes to shopping in a clothing store, purchases a shirt with probability 0.3. The customer will purchase a pant with probability 0.2 and purchase both a shirt and a pant with probability 0.1. So let's look at what is S. S is the event of a customer purchasing a shirt. So what is the probability of S? What is the probability of a person purchasing a shirt alone?
0.3.
0.3.
0.3.
3. What is the probability of a person purchasing a pant alone?
0.2.
0.2.
What is the proportion of customers who are purchasing a shirt and a pant?
0.1.
1.
0.1.
0.1. Okay. So what is the proportion of customers who are purchasing either a shirt or a pant?
Complement of either a shirt, like
0.4.
Either. I'm not
It
asking.
is a union.
I'm asking probability
0.4.
of people
0.4.
purchasing
0.4.
either a shirt or a pant is 0.4
0.4.
plus 0.2 minus
Point.
0.1, which is 0.4. Agreed? Now I want neither a shirt nor a pant. So what is neither a shirt nor a pant? It is
Complement of this.
Complement of this
complement. So I
0.6.
know that this is the same as probability of S1 minus probability S union P.
Right.
I already know what
0.6.
is probability S union P. So this is 1 minus 0.4. So what is the answer? It is 0.6. So this is a simple thing where we have applied where I can find out the probability of the complement of an event, use that to define what I need and compute the probability of neither shirt nor pant to be 0.6. Is this clear? Okay.
Yes.
Again, the framework we have used is just identify. So break it down to simple events like shirt, buying a pant, both of them together. Then neither, to write it as the complement of the union and just get hold of the solution. Is this clear? Yeah?
Yes, ma'am.
Yes, ma'am.
Now, one of the things which you keep coming across is the notion of equally likely outcomes. Equally likely outcomes, for example, when I roll a die. How many outcomes are there when I roll a die?
6.
6. In a fair die, the chance of getting 1 is the same as chance of getting 2 is the same as chance of getting 3 or 4 or 5 or 6. In other words, all of them are said to be equally likely to happen. And I can write that as the probability of 1 is the same as probability of 2 is same as probability of n. Now, if each of them have the equal likelihood of happening, the probability of I happening is nothing but 1 by n. And if an event has n of these outcomes, then the probability of A, for example, we immediately saw that if I roll a die, and I am looking at only odd outcomes, well, how many outcomes of S are in A? 3. So 3 by n, which is 1 by 2, is the probability of me getting an odd number. So that is another way you will keep looking at is you need to understand the concept or the place where I am looking at equally likely outcomes. Okay, so let's look at an example. Again, I'm rolling a die. A is the event that the outcome is odd. What is the probability of A happening?
Half.
Suppose B, it is half. B is the event that the event is greater than 4. What is the probability of B happening?
1 by 3.
1 by 3.
1 by 3. Very good. C is the event where the outcome is greater than 4, is either odd or greater than 4.
1 by 2.
1 by 6.
What is probability of C?
Okay.
It is either
1 by 6.
the probability of A or B, A union B. Is that right? C is nothing but probability of A union B. Yes or no?
Yes, ma'am.
Yes.
Yes, ma'am.
What is now probability are A and B disjoint?
2 by 3.
Are A and B disjoint?
No, no,
No,
ma'am.
ma'am.
No, ma'am, they are
What
not
is the
disjoint.
probability of A intersection B?
1 by 6.
1 by
1
6.
by 6.
So now what is the probability of C? It's 3 by 6 plus 2 by 6 minus 1 by 6, which is 4 by 6. Is it
2
clear?
by 3. Yes, ma'am.
2 by 3. Okay. So now you can see that what we have just introduced interpretations of probability. Primarily, we looked at the probability axioms, the addition rule of probability, and how we apply the addition rule of probability for certain problems. Again, you might say that how do I understand? See, always remember, start with the basics. If you're able to get your sample space and identify your events properly, getting a probability most of the time is not, it's again, I will not give an algorithm how to go about a tricky question. You should start looking at the problems in a structured way, and most of the times that should work well. So the next thing that we are going to look at the notion of conditional probability. Now, what is conditional probability? See, for example, I am tossing a coin 2 times. What is my outcome? It is head, 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 tail, tail, head, and tail, tail. Now, suppose I do not know anything about probability itself. Okay. And I give you a coin, I keep asking you, toss it. Do you think that the chance of you getting a head in the second toss depends on whether you had a head in the first toss? Is
No.
it dependent? Or is it
No.
independent?
No, ma'am.
It's independent.
It is independent. So even before notion of probability itself, you are saying something, you are telling it is independent. So what do we mean by this notion of independence? So let's look at something which we refer to as a probability tree. I'll just show you what is a probability tree. So I have a first toss. What is my first toss? It could be either a head or tail with equal probability. This is the outcome of my first toss. In my second toss, again, what are the possible outcomes? This is my first, this is the second. What are the possible outcomes in the second toss?
Head and tail.
It's again head and tail. Again, this is head and tail. Okay. Now, the outcome of the second toss. Now, what is the chance with which a head can appear in the second toss?
1 by 2.
What is the chance by which a tail can appear in the second toss? 1 by 2.
Same 1 by 2.
This is again
1
1
by
by 2. This is again 1 by 2. Till here, is it clear?
Yes, ma'am.
Right? Okay.
Yes,
Now,
ma'am.
let me tell a similar thing. I have a bag, okay, with 4 red and 3 white balls. Okay. I'm picking up one ball at random. What is the chance of me getting a red ball? What are the possible outcomes? It could be a red ball or a white ball. Is it clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Listen to the experiment. I'm picking a ball at random and I'm replacing that ball. What is the chance with which I get a red ball?
4 by 7.
4 by
8.
4 by 7, right?
Okay.
And this is 3 by 7. I'm replacing it. I'm doing it second time. What are the possible outcomes in my second time?
4 by 7 and 3 by 6.
Again 4 by 7 and 3 by
Again,
7.
it is red, white, which is again
4 by
4
7.
by 7 and 3 by 7.
Again, here it is a red. This is white. This is 4 by 7. This is a 3 by 7. Now, I am choosing a red ball and I'm not replacing it. Okay. So, what is the chance here? This was 4 by 7.
4 by 7.
This was
3
3
by
by 7. Now,
The
again,
red-
I am choosing the outcomes are red and white. But what is the chance with which I have a red here?
3 by 6.
3 by 6.
3 by 6.
4
3 by
minus
6,
3
ma'am.
by
3 by
5.
6.
And this
2
is
by 6.
3 by
2 by
6.
Ma'am,
No,
3
three-
by 5.
3 by
no,
3
no.
by 6 only.
This is 3
3
by
by
6.
6 for both.
3 by
3 by
6.
6 for both, right?
Yes,
Because
yes.
I have a red ball here. If I already have a red ball, I have only 3 red and 3 white to choose from, right?
Right.
Okay. Here I have 4 red and 2 whites to choose from. So this is 3 by 6, 3 by 6. This is, what would this be?
That would be 4 by 6
4 by 6
and 2 by
by
6.
6. So if you look at it, here the second draw of my red, did it depend on whether I had a red or getting a red in the second toss? Did it depend on whether I had a red in the first toss or not?
No.
In this case.
No.
Whereas here, the getting a red in the second toss, it depended on whether your first was a red or a white. Is it clear?
Yes, ma'am.
Yes, ma'am.
So
Yes, ma'am.
I have certain events where it could be dependent and certain where it is not dependent. Is it clear? Yeah.
Yes, ma'am.
Yeah, clear, ma'am.
Yes, ma'am.
Okay. So now this is where we introduce the concept of conditional probability. So the way I'm going to talk about conditional probability is if H1 is a toss on my first throw and H2 is a toss on my second throw, then I would like to know what is the chance of my second throw given the chance of my first throw. This is what I refer to as given. Okay, it is not divided, it is conditioned upon. So the way I can represent the notion of conditional probability is, I know that this event has happened. Probability of E happening conditioned on F has happened. So E is this event, okay? I already know F has happened. So the probability of E happening conditioned on F happening is nothing but this intersection of probability of E intersection F divided by the total probability. That is what is defining the conditional probability. E happening conditioned on F is this intersection divided by the total probability of F. Is this clear? This is the definition of conditional probability. Is it clear?
Yes, ma'am.
Right? So once I know the definition of conditional probability, the idea is I have written this probability of E conditioned on F. This is to be read as probability E conditioned on F is the intersection of probability divided by the probability. I can write this probability of E intersection F is probability of E conditioned on F into probability of F. So what this says is probability of the intersection is the same as probability of E conditioned on F into probability of F. This is similar to your union of F rule, which says probability E or F happening was probability of E plus probability of F minus probability of E intersection F. Here I have a rule which says probability of E and F happening is probability of E conditioned on F into probability of F. Is this clear?
Yes, ma'am.
Right?
Yes, ma'am.
So the conditional probability rule gives rise to a multiplication rule, just as I had an addition rule earlier. Now I have a multiplication rule which is helpful in computing the probability of the intersection. And what is the probability of the intersection? It is probability of E intersection on F is equal to probability of E conditioned on F into probability of F. That is what I refer to as my multiplication rule. Till here, is it clear?
Yes.
Yeah, ma'am.
Now I can extend this multiplication rule to what I refer to as a generalized multiplication rule, which is giving me the probability of intersection of n events, which is probability of E1 into probability of E2 given E1 into probability of E3 conditioned on E1 and E2 has happened, so forth. Okay, so this is what we refer to as a generalized multiplication rule. Now, just as when we talked about addition rule, we had the notion of disjoint events to be very important, and we said that the probability of a union of disjoint events is the sum of the probabilities. When I talk about the multiplication rule, the notion of independent events is very important. What do we mean by notion of independent events? I know from a conditional probability definition, probability of E intersection F is probability of F into probability E intersection F. This is from my definition, right? Would you all agree? Yes?
Yes, ma'am.
Now, if E is independent on F, what would be probability of E conditioned on F? If E is independent on F, what is probability of E conditioned on F? What would happen to this? E
PE.
has nothing to do with F.
Yes,
It would
ma'am.
be probability of E itself, right? So probability of E intersection of F, if E is independent, if E is independent on F, is probability of E intersection F is probability of F into probability of E. So when I have two events, I say two events are independent if probability of E intersection F is equal to probability of E into probability of F. That is, the probability of the intersection is product of the probabilities. Analogous to, if two events were disjoint, I said probability of the union is the sum of the probabilities. I say two events are independent if probability of the intersection is the product of the probabilities. Two events that are not independent are called dependent events. Something which I want to note here is this is an if and only if statement for only two events. That is, if and only two events E and F are independent, if and only if the probability of the intersection is the product of the probabilities. For more than two events, we have the notion of pairwise independence. You can refer to the lectures, we talk about it. But mostly when we are talking about two events, this probability of E intersection F is equal to probability of E into probability of F becomes a, if necessary, and sufficient condition. Moving forward, when we talk about the conditional probability, one of the key things that we have in conditional probability is the Bayes theorem. Now, what does the Bayes theorem tell us is the following. Before even going to Bayes theorem, the Bayes theorem states the following, that if I have A1 and A2 as mutually exclusive events and exhaustive events. So let's look at understanding what this tells us. Suppose I have the following. I have three mutually exclusive events Let me call that E1, E2, or again A1 and A2. Okay, I have only 3 events, so let me do as 3 events first. I'll extend that to more than 3 events. So I have A1 and A2. There's no intersection and they're collectively exhaustive. Okay. A1 union A2 defines the entire space. Is this clear? Now I have an event B here. Okay. Now can I write B as B intersection A1 union B intersection A2? Can I do this?
Yes, ma'am.
Okay, right. When I can write B as B intersection A1 intersection A2, what can I say about B intersection A1 and B intersection A2? Are they mutually exclusive?
Yes.
Yes.
Yes,
Yes,
ma'am.
ma'am.
So would you
Mutually.
agree that I can write probability of B as probability of B intersection A1 plus probability of B intersection A, because I can apply the addition rule? They are mutually exclusive.
Yes, ma'am.
Now, what do I know from a multiplication rule of probability B intersection A1? I know this is probability B conditioned on A1 into probability of A1 plus probability of B conditioned on A2 into probability of A2. Yes or no?
Yes, ma'am.
Right? So if I want to know probability of B, I have this probability of B is equal to probability of B conditioned on A1 into probability of A1 plus probability of B conditioned on A2 into probability of A2. Is this clear? So
Yep.
let's look at an example. Suppose I have 3 manufacturing plants. Okay. And this supply 20%, 30%, and 50% of all shock absorbers used by a certain automobile manufacturer. So what are the 3 mutually exclusive and exhaustive events here?
Manufacturing from ABC.
ABC.
So A is giving me 20, B is giving me 30, and C is giving me, so probability of A is
0.2.
2.
0.2.
Probability of B is
0.3.
3. Probability of C is
0.5.
0.5.
Here all of us are clear, and they are mutually exclusive because I have a part that can come from both A and B?
No, no,
No,
no.
no.
Part can come either from A or from B or from C. Till here is it clear?
Yes, ma'am.
Now records show that the percentage of defective items produced by A is 3%, B is 2%, C is 3%. So if I have 100 units, I have a subset of defective items. Is that right?
Yes,
This
ma'am.
defective item can come either from A, or it can be from B, or it can be from C. Is that clear? Now, what is this 3%? It is probability of defective given A, or is it probability of defective and it is from A?
Probability of defective given A.
Given A. That is what we need to understand. Is that clear?
Yes, ma'am.
Okay. So what is the probability of defective given A? This is 0.03. I have a probability of defective given B is 0.02. And I have a probability of defective given C is 0.01. Okay. Now imagine I am in the manufacturing plant. I have mixed up all these parts together. That is parts coming from A, parts coming from B, and parts coming from C. I have mixed up all together. Okay. I pick up one item at random. I want to know what is the chance that is defective. Is the question clear?
Yes, ma'am.
Yes, ma'am.
Okay. So the first question I want to know is what is the chance that the item I picked is defective? Now, if I apply my what I refer to as the law of total probability, this is probability it is defective and it is from A, from this portion, or it is defective and it is from B, this portion, or it is defective and it is from C. Would you all agree?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Which is same as probability it is defective given A into probability of A, plus probability it is defective given B into probability of B, plus probability it is defective given C into probability of C. Is that right? So this is
Yes,
what
ma'am.
we refer to as law of total probability. Now, do I know what is probability D given A?
Yes, ma'am.
Do I know probability of A?
Yes.
Do I know
Yes.
probability D given B?
Yes.
Yes,
Yes,
ma'am.
ma'am.
I know what is probability of B.
Yes,
I
ma'am.
know probability D given C. I know probability of C. So the first question is, what is the probability that a randomly chosen shock absorber is defective? I can get the answer to it from the law of total probability. Is this clear?
Yes, ma'am.
Yes, ma'am.
Okay. Right. Now, let me again go back to this. Suppose I pick one item at random. What is the chance that item has come from A?
0.2.
0.2. What is the chance it has come from B?
0.3.
What is the chance it has come from C?
0.5.
0.5. So these are what we refer to as prior probabilities. Okay, that is, I pick up one item at random. I know that the chance that it is from A is 0.2, from B is 0.3, and C is 0.5. These are what we refer to as priors, right? Now I am adding some more information. I pick up an item at random and I notice it is defective. Okay. Now, what is the chance that it has come from A? So that is probability A given D. Would you all agree?
Yes, ma'am.
Right? So now, first is I obtain what is the law of total probability, which is probability of B, which is probability of B given A1 into probability of A1 plus probability of B given A2 into probability of A2. Now, if I want to know A1 conditioned on B, this is what I refer to as the posterior. From a definition, I know this is probability of A1 intersection B divided by probability of B, right?
Yes, ma'am.
Probability of A1 intersection B, it is B given A1 into probability of A1. And here I already know that this is probability of B given A1 into probability of A1 plus probability of A2 into probability of... Is this clear? This is what is referred to as the Bayes theorem. So applying again to a defective, I know what is probability of defective. What is probability of defective? D given A into probability of A plus probability of D given B into probability of B plus probability of D given C into probability of C, right? This was my total probability which gave me what is the probability of a defective. Till here, is it clear?
Yes, ma'am.
Yes.
Now I am saying that I again shuffle everything. I notice that whatever I have picked up at random is defective. I want to know what is the probability that it came from A. Okay. What was the prior probability? I know prior probability of A was 0.2, probability of B was 0.3, probability of C was 0.5. These were my prior. Now I'm asking the same question, but I'm giving you extra information. Okay. So one of the most, so what would this be? Again, from my definition, this would be probability of A intersection D into probability of D. Do you all agree?
Yes, ma'am.
Now, this numerator is going to be probability of D given A into probability of A. The denominator is going to be probability of D given A, probability of A, plus probability of D given B, probability of B, plus probability of D given C, probability of C. So I can obtain the posterior probability of A given D by applying what is called the Bayes theorem. Is this clear?
Yes.
Right? So one of the most famous examples of application of this conditional probability or the Bayes theorem is what is called the Monty Hall problem. How many of you watch game shows? So there are 3 doors. Okay. Door 1, door 2, and door 3. Okay. Behind 2 doors, there is a goat, and behind 1 door, there is a car. I repeat, behind 2 doors, there is a goat, and behind 1 door, there is a car. The first thing is you are allowed to choose a door. Okay. What is the chance that you will win a car?
1/3.
1/3. Agree? Okay, suppose you choose a door. What is the door you are going to choose? Suppose you have chosen door 2. Okay. Right? Suppose you have chosen door 2. I open a door and show to you which has a goat. Because as a host, I know where is the door, right? And definitely whatever door you choose, I will have a door where I can show you a goat, yes or no?
Yes, ma'am.
Right?
Yes.
So suppose I open door 1 and there's a goat behind. Now you are given an option to swap this one. That is, would you continue to choose door 2 or do you think you will choose door 3? Is the game clear?
Yes, ma'am.
Is the game clear? What do you think you will do? Would you swap your option or would you continue to have your option?
I will swap
Why?
because now its probability is 1/2 of getting car,
How?
because one of the option is gone and there is only 2 option left.
So you can actually argue using the conditional probability, that is probability of me winning given that some extra information. See, the prior probability is probability D1 equal to probability D2 equal to probability D3 equal to 1/3. Okay. Now I'm giving you some extra information. Now I want to know what is the chance that it will be behind D2 and what is behind D3, and rightly pointed out the probability would be higher if I swap, and most often the swapping option is exercised, and you can actually show through conditional probability how this happens. Is it clear? Right?
Yes, ma'am.
The Bayes theorem is a very important theorem. When you have to apply the Bayes theorem, the 3 key things or the 2 key things is, one, identify what are the mutually exclusive events. That is extremely important. Again, go back to this problem. The mutually exclusive events here were that I could have a shock absorber coming either from A or from B or from C. This is mutually exclusive and exhaustive. Is that clear? The next thing is identify what is the event of interest that is having an intersection with all these here. In this example, it was again the defective item. Okay. And then you see that what is the probability that A was happening earlier, that was a prior, and how it was revised with the new information that whatever you have picked is a defective item. That's where I have applied the Bayes theorem to get probability of A conditioned on B. Is this clear? Any
Yes, ma'am.
questions? Is this clear, please?
Yes, ma'am.
So
Yes, ma'am.
this was about the Bayes theorem. Now going back to probability trees, we have already done this. Probability tree is a very helpful way to understand the multiplication rule. And what is the multiplication rule? The probability of your conditional, how are you going to look at your conditional probability? So if I'm having a head and tail in my first toss and with probability 0.5, 0.5, the probability of your second toss is head, head and head, tail. So what are your eventual outcomes? It is head, head, it is head, tail, tail, head and tail, tail. What is the chance with which head appears here? This is a half and a half. So I know that the probability with which HH appears is half into half, which is 0.25. This is also 0.25. This is also 0.25. This is also 0.25. And this is just your probability of A intersection B is probability of H into probability of H, and they are independent. On the other hand, if I have something of this kind, now I have a 4 white and a 3 this one. I take a black ball. I am now just changing the experiment that you could either go to bag 2 with 3 white and 6 balls. Okay. I'm telling you could go to another bag. It need not be the same bag. And bag 2 here is 4 white and 5 balls. Then again I can choose a black or a white. I can choose a black or a white with different probabilities. I see that here my final B1 intersection B2 is 3 by 7, 6 by 9, 3 by 7, 3 by 9. And you can see that the probability of B1 intersection B2 can be written as probability of B1 into probability of B2 conditioned on B1. And this is what we have as a multiplication rule. Okay, what is the probability of B1? It was 3 by 7, which I have here. Probability of B2 conditioned on B1 is 6 out of 9 and 6 by 9. So probability of B1 intersection B2 is nothing but probability of B1 into probability of B2 conditioned on B1. So you can see how I can apply these rules. In first case, I had independent events. Here I have dependent events. Okay. Any more questions? I think I have done with whatever I came prepared with. We have about 10 minutes. I can take any questions that you have for the next 10 minutes. Yeah. You can use the chat box also. Any questions? So I'll just go through a few chats. Are there video solution available for activity questions? I think I'll allow Swati to answer this. Any other questions? Any other clarifications?
Ma'am, I have one question.
Yeah.
Ma'am, when we are when we come across a question which is based on base theorem, so what we do is that in the denominator part, we find the conditional probability in the denominator, right?
Pardon?
Ma'am, for the base theorem part, the
Yeah,
denominator
let me
part.
go to the base theorem. 1 second. Let me go
Yes.
to the base theorem.
Yes, ma'am.
Yes.
Ma'am, the denominator part should always be equal to the total conditional probability, right?
What do you mean by total conditional probability? This is the total. See, the denominator. See, instead of looking at numerator or denominator, okay, base theorem basically, I think the best way I would understand base theorem is to look at this. Okay, what were the, suppose you're having shock absorbers coming from all the 3 plants, okay, to this one particular place. You're mixing all of them. You pick up one at random. What is the chance it would have been from A? Yeah?
Yes, ma'am.
What is it? It is 0.2. Chance it would have been from B is 0.3. Chance it would have been from C is 0.5.
0.5.
And this is mutually exclusive. And I know that if I pick up one at random, it would be either from A or from B or from C. Till here, is it clear?
Yes, ma'am.
These are, so first thing I need to understand is what are my mutually exclusive and exhaustive events. So have I defined that?
Yes, ma'am.
Now the second event is I have a defective item. Now if I have picked up a defective item, it could come from A, or it could be defective and it is from B, or it is defective and it could be from C.
Yes, ma'am.
Right? So I know that this item, defective item, could be either from A, or it is defective and it is from A, or it is defective and it's from B, or it is defective and it is from C. I know the conditional probabilities are given to me here. So you could either have the conditional probabilities or you could have the probability D given A. What is given to me here? Conditional probabilities. What are the conditional probabilities? This is 0.03. D given B is 0.02 and probability of D given C is 0.01. Okay. Now you're talking about the denominator. So the first way to understand it is what is the law of total probability. That's why in this probability, this problem, I said First, you tell me what is the chance that any item you pick up at random is defective. This is the law of total probability. How can an item be defective? It could be either from D and it is from A, or it is defective and it is from B, or it is defective and it is from C. This is what is my law of total probability. Till here, is it clear?
Yes, ma'am.
This is what I'm getting as probability D given A into probability of A, plus probability of D given B into probability of B, plus probability of D given C into probability of C. This is what we refer to as the law of total probability. Okay?
Okay, ma'am. Yes, now clear.
Total sample space, if you can think like
Total probability, and this is coming from, see, the three key things are mutually exclusive, collectively exhaustive, and this D has an intersection with this. How am I writing this D? I'm writing as D intersection A, union D intersection B, union D intersection C. That's why I'm
Right.
able to apply the additional rule.
Right.
Now I'm looking at posterior. Posterior is okay. What is the chance that I have extra information that it is defective? What is the chance it comes from A? That's where I'm applying the base theorem. Is it clear?
Yes, ma'am.
Okay, that's how you can do it. Any more questions? Any more questions, please?
Is it the session being recorded? By when can we expect the live recording for this?
Swati or Prerna, can you answer the question?
Yes. So the session is being recorded, and the recording link, you can find it on the calendar.
Okay. The PPT as well?
Yes.
Okay. Thank you.
Okay. Any more questions? Okay, if there are no more questions, thank you all. Wish you all the best. Okay, thank you all.
Thank
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Bye. All the best. Yeah, thank you.
Thanks, ma'am.
Thank you.